We're going to explain about the Sufix trees and their application in string algorithms. Our team are Oscar, Samit, and Ruben. Abstract. The Sufix tree is a data structures using two different search operations within a string. Its main objective is to search for substrings, data comprehension, search for palindromes, among others. For example, we can use this algorithm or this tree of suffixes for search into the full text or a big books. We can found some works into this book, or for example for large sizes of I don't know, maybe items for supermarkets for frequently works into the something. I'm going to talk about the history of suffix tree. The first suffix tree were created in 1995, and after in 1997, Magritte and Chen make one algorithm of suffix tree. For other types of algorithms have been created after 1995. What is the sophistry? The sophistry is a data structure that serves to store a string of characters with the pre-processed information about internal structure. The suffix tree take the pre-processed information for the search into the big spaces, but is necessary have the suffix for a scan of the tree.
Now I will explain the creation of the suffix tree. In this example, we'll use the $sign to express the end of the word, and assign a number in each letter as in the image. Next slide, please. Okay, in the first image, I see the word banana, and now we erase the first letter, and the new word is anana. This is the second branch of the suffix tree. This is in the image 2, and now with the new word anana, I erase the first letter and create the three tiers branch. This is the new word is anana, okay, and repeat this process for every letter. In the image 4, we have the anana word. This is the same of the second branch, and we need to use this branch to create a new branch from this. In this case, we erase the first A and have two branches. One for the end of the word, that is the right branch, and another for the NA and $sign. and repeat this process with every part of the word. At the end, we have the result of the process of the suffix tree, and this is the end of the this is the result. Next slide, please. Okay, lowest count and fastest count represent the form to the algorithm. Find some letter or part of the word. The fastest count is when we know who want to find, and they use this information for jumping from node to node, and it's very fast. That the slowest scan go to the end of the to every leaf, and compare every result of the suffix tree.
Now I'm going to explain about the change algorithm for the imagine of the left is the code for the algorithm, the change algorithm, and the table of the right we have five. For example, in this case, I talk about the example for a supermarket. That's why I have 4 transactions and 5 items. So I will explain the algorithm. In the first line of the algorithm of the left, you can see for each basket is for all the transactions. For example, if you have all transaction or 4 transactions, you have one basket for each transaction. For each transaction or for each basket is all the code. In the third line, you can see for each item is how many items repeat in all transactions. For example, if you found one item or item number 1 repeat in 2 or 3 times, you can put for each item. In this case, for each item, if for 1, add 1 2 items in the count. If you found an other time the same item, this item is 1 plus. In the fourth line, you can see for each pairs of items. In this case, after I will explain how can I know found some pairs of the items. When you found the pairs, you can put in this part for how many times this pair repeat in the whole transaction, and the hash, the pair of bucket, is the step 1 for applied this algorithm. In the past one, or step 1, we need to know how can I found what is the minimum support. For this case, the minimum support is 2. The minimum support is the 50% of the transaction. For this case, we have 4 transactions. Our minimum support is equal to. In the table on the left, we have 4 transactions. Each transaction have any items. For example, the transaction 1 have item number 1, item number 3, item number 4, and item number 5. in the same in the another transaction. For example, the transaction 2 just have 3 items, 2 and 3 and 4. On the item, on the table of the right, have a item set and 5 items, and what is the minimum support per item. For example, the item 1, the support is 2, while because you can find 2 times to repeat in the all transactions. Number 1 repeat in the transaction 1 and the transaction 3. That's why you can find in the table of the right, in the item 1, the support is 2. In the same way, you can put the item 2 and item 3 and item 4 and item 5. For example, the item 2 you can find in the all transaction on the left, in the table on the left, 3 times. In the transaction 1, transaction 2 and transaction 3, the support of the item 2 is 3. Now, this is the same step 1. How many times repeat the pairs? Or how can I know found the pairs? When you see the table of the left, you can make the pairs. For example, in the transaction 1, we have 6 pairs. 1 and 3, 1 and 4, 1 and 5, and 3, 4, and 3, 5. This is the all pairs in the transaction 1, and the transaction 2 we have 3 pairs, and the transaction 3 we have 6 pairs, and the transaction 4 just have 1 pair. The numbers behind the pairs is, for example, in the below the pairs 1, 3, you can find a number 2. Why number 2 is how many times they repeat this pair in all transactions. For example, the pair 1, 3 we repeat in 2 times in the transaction 1 and transaction 3. The same way you can put the how many times for another pairs. This is the last one, the last step is to apply the hash function for each bucket and its count. The number of the bucket or item is 5 items, and the count is the how many times they repeat this this item in the all pairs. For example, the backslide. In the right side, we have for this example, just you can find number 1 and number 2. Another example, you can find, I don't know, maybe 1, 2, 3, 4, 5. For this example, just 1 and 2. How many times repeat the number 1? 1, 2, 3, 4 times you can repeat this item. And how many times to repeat the number 2? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 12 times we repeat the same number. So how for the item 1, 4, for the item 2, 12, for the item 3, 0 times, and 4, 0 times, and 5, 0 times. This Shen's algorithm is for looking for the frequently times you can find some items, some work, some things you can find frequently in some works.
Okay.
Ready. We're gonna explain about the migrate algorithm. We recall that the suffix tree are a data structure extremely useful to search data in longest text. We make the sketch of the migrate algorithm, and we start with a word. Next slide. We take, for example, the word the string x that are equal to ABAAB. All right, we start with the back slide, please. We start with the first step of the algorithm, who are construct the tree, the first tree. We remember that the construction of suffix trees are iterative form to create trees. The first step are with the first letter of the tree. In this case are the A letter. Next. Alright. In this case we make the for cycle where I are equal to 1 to n. N are the cantidad of letters in the string. Alright, in the first step are 1 if the head that are the the top of the branch are null. Then next step we add a branch and make a log scan, and the tail are the same word that the branch less the first letter. In that case the word say BAAB, and repeat the for. Alright, in this case the head is again null. The tail now in this case are the branch number 2, and the new branch are PA because the top are the head A. Next. Again, and we do the third tree. We repeat all the procediments. Next. Alright. The parent in this case are all the three, the initial head, but the next head in we are parados, ven, are B equal to A, and here 6 with head. Next, but with U are not equal to null, then we make a fast scan, but else W are equal to a fast scan who makes from the top to all the branch. Next. Right. And now if W is in a edge, and in this case are here where the word B, head are equal to E plus 1. Next. And add a note if it's necessary. Next. Alright. And if the head in this case are equal to W, and in this case are not here. Next, we add a leaf, and head are equal to A plus 1. Next. Okay, and we make the next tree, the tree number 4, and we repeat all the process. Alright, we are the last tree. We are all the suffix in the word. Next.
The application of the suffix tree, they are used to find the longest repeat substring, the find to the longest palindrome in a string. And another use is to find part of the ADN chain, because this algorithm is very fast to respond or to show the results. This is the application, the most common application of the suffix tree. Listo.
Please.
And for finally, we explain the conclusion of this paper. Can be understood by the reading that a suffix tree are a data structure that applies to or in a different things, focused with the processing of very extensive strings in a set of subtrees in a large search structure. Thank you.
Thank you.